Hi, I'm Tom Bliss.
And I'm Patrick Lewis.
So for our Applied Deep Learning project, we did the Food Segmentation and Classification Challenge on AICrowd.com. The purpose of the challenge is, given a bunch of images of food, we want to segment and classify each type of food on a plate or in just in the image. And it's a multi-class, multi-instance problem, meaning there could be multiple types of food in the same images, as well as multiple instances of the same food in the same image. So this data set that we're given contains about 5,800 images. A lot of the images are regular images of food, not what you might see on TV or in a menu, more like what you would actually get when it's on your plate. There's about 40 food classes, and the training and validation are labeled for segmentation and classification. We thought about two different ways to approach the problem. One, we create one model that will do segmentation and classification at the same time. The other way we thought is maybe we do two models, one that segments images, one that classifies the segmented images. We decided that the first approach was better. It was a simpler approach. It avoided cascading errors. For example, if we were segmenting something and we thought, oh, this is food, but it really wasn't food at all, then it became very problematic. What would be the correct answer if the segmentation got something completely wrong? And it's just a simpler approach and an easier way to think about. However, although this was simpler, this did not come without any issues. Obviously, the size of the data is a lot bigger when you have 41 classes versus 2 classes that you're trying to segment on. We tried using the tf.data.dataset commands to load in the images as we were iterating through the epochs. Unfortunately, that caused a really long time, about an hour per epoch, and which really didn't allow us to do any model testing or any experimenting, so we kind of had to drop that. To fix this, we decided to change from categorical to sparse categorical loss and then choose the most common class when there was overlap. That's essentially how we got around this issue.
So in terms of what we actually chose for model, we decided to use a model that's based off the UNet architecture, and this was done because we had read some literature that had done similar problems in the medical field and was very successful. And the basis of the UNet model is essentially to have one half of the model extract features down to the base level of convolutions. In this case, we used ResNet 152 version 2, and then have the other half essentially upsample those base level features into something that is able to classify data in kind of an image format. So we experimented around with the UNet a little bit. One of the key experiments we did was to try different feature extraction models, and we tried different ones that came from Keras. We tried the DenseNet, MobileNet, and ResNet. Ultimately, ResNet gave us the most consistent results, both in terms of metrics and in terms of when we spot checked predictions. It seemed very visually consistent, so we decided to go with that. We started off with building a kind of simple prototype model where we identified whether food had broccoli in it or not, and this trained only on data that had broccoli in it. It worked pretty well, but as we tried to expand the model to the other 39 classes, the accuracy and the predictions started getting worse, and that led to a roadblock in terms of shifting our model from classifying a single class to many classes. We initially found that the model would just predict 0, which means no food at all, and it would do that either more often than it should or just totally would do it for all of the data. And this is because approximately 72% of all the pixels are the 0 class. And to remedy this issue, we wrote a custom loss function, and we set the weights of that custom loss function to a variety of different things. We experimented with 1 over the number of occurrences, 1 over 10, 1 over 20. And we'll see in the code in a little bit which one we actually ultimately used. In terms of results, this allowed us to run our model successfully. It actually started giving back successful predictions. As you can see on the screen right here, we have an image of salad, and it's predicting salad green as the output. And with every prediction, we would get a matrix of 256 by 41. And the 41 is going to be essentially that image with an output of a softmax function where we see how likely the model thinks that pixel belongs to that image. And ultimately, the accuracy on our holdout set, which is a set that we didn't touch at all, is 83.5% across all pixels, which is great. And we're going to get into a little bit. Accuracy isn't necessarily the best way to determine model performance in this case, but we're fairly happy with this model, and we think that it performed well.
So here's our code. First thing we do is import libraries as well as mount the Google Drive. We load in the data using the Cocoa functions. These work well because the annotations are in Cocoa format, so it's really easy to read off of them. We create a function that will plot an image based off the image ID, and then we randomly choose 5 images and just go ahead and plot them. This gives us a good sense of what the data looks like, what to expect when we're predicting and when we're fitting. Next, we got to load and clean the data. Unfortunately, the categorical IDs that are given are not in a good format. They're sort of arbitrary, 1,000 to like 9,000 number digits. It doesn't really make much sense for us to do it that way. So what we do is we order them by most common image, which we use later. That's how we determine what's the most common image when we're dealing with ties, and then we say that the class is where the image is, where the category is in the list. So we check if the training data hasn't been saved, the validation data hasn't been saved. If the training data has been saved, we go ahead and start iterating through the images. We load the annotations, we apply the annotations and save them to Y. We do a similar thing with X. And then we do sort of the same thing with the validation data as we do with the training data, assuming it is missing.
So in terms of building out the model, again, we're using a kind of a UNet model architecture. We started off by loading in the ResNet model, in this case ResNet 152 version 2. And the first thing we want to do is get the essentially the layer names for the activations that we want to extract. So we get all the layer names, go through the ResNet model and actually extract the activations. And this creates something called our down stack, which is essentially our feature extraction. And then on the up stack, this is the classification side of the model. We're using something called pix to pix. And what we're doing is we're upsampling based on those base features that have been extracted. We're upsampling to the point that we're able to make a classification. And in this function, we actually we create the UNet model. So we start with the down stack, we have the up stack, and we have our last layer, which is essentially a conv 2D transpose within a softmax activation function. And this will return an image that has gone through the softmax function for each of the inputs and each of the classes as well. So it's going to be 256 by 41. So we create our 41 class UNet model. Here we have a little bit of a visualization. We have our ResNet model up here, and you can see it's actually connected to each one of the classification layers as well. And this is kind of like standard in the UNet architecture. And then finally, we have this conv 2D transpose, which does a final prediction. Now we needed to also do a custom loss function. We started off by going through and getting the number of pixels for each class. We found that the 0 class is about 73%. And we can see that the other classes have a very low percentage based on all of the data. Now, we ran a couple experiments. In this case, we have the 0th class being weighted at 1/5. We've also tried 1/10, 1/20th, as well as 1 over the number of occurrences. But in this case, we found that 1/5 works very well. And this is assigning the weights. We then go down to the actual loss functions. We couldn't use the traditional Keras architecture, unfortunately, so we had to use kind of our own custom loss function, which assigned the weights to the models. Here we go through just the traditional training, use atom accuracy, and we did it for 10 epochs. When looking at the model output, we see that the accuracy actually goes down as epochs go up. Now this is very counterintuitive. You'd think that the accuracy would go up at least for a while. But in this case, it actually made sense because we changed the loss function to not be traditional. What we wanted is that the model would actually overpredict food and underpredict the 0th class. because we thought it would be more important for the model to predict food than it would be for the model to be accurate on the 0th class. And this, of course, is because of class imbalances. So in this case, actually going down actually makes sense, as in the model is getting less accurate on the 0th class, but is actually getting more accurate predicting the foods. And this is something that we played with a little bit. As you can see, the loss makes a little bit more sense. The loss is continually going down, but finds around 6 epochs is minimum.
So to ensure that it's all working well, we decided to make a few predictions on the validation set that we did not touch at all during training. So we go ahead and load in the validation set, and we make this custom function to test, and we randomly choose 5 images. Here's an example of one. This is some sort of drink, and it's predicting coffee with caffeine, white coffee with caffeine, as well as tea. Here's another. It's predicting tomato, mixed vegetables, and salad green, which seems pretty reasonable. And then finally, here's a piece of bread. It really thinks this is a piece of bread. For whatever reason, it thinks it's water, but it also thinks it's bread wholemeal. But we're happy with the results since it's overwhelmingly predicting this as bread white, which is obviously what that is. To just ensure that we're not just getting a few good random predictions, that we're actually creating an accurate model, we go ahead and evaluate the scores on the actual validation data. And we're pretty happy to report that we have a validation loss of about 0.13 and an accuracy of about 83.5. Thank you guys for listening, and I hope you have a great day.